Yes, today we discuss the introduction to the context-free grammar, which is very essential part of our curricula. This is just after the regular grammar, then the context-free grammar comes. Regular grammar, you cannot have any programming language. So for making a programming language, you need opening brace and closing brace. Like in C, you have the two braces within the program. So you need that. So that is, you need it. Most of the programming languages comes under this context-free language, and there's a main two part. One is deterministic context-free, which can be recognized by deterministic PDA, deterministic pushdown automata, and this non-deterministic. So this context-free languages is a huge range of languages. Then comes the context-sensitive. We'll come to this. And here I intentionally choose one particular picture on Noam Chomsky, who has given this various types of grammar. That is type 3, type 2, type 3, type 2, type 1, type 0. Noam Chomsky, he has done a seminal work from 1956 onwards, and he's still relevant on various issues. He has always given his strong opinion. Like here I have taken a picture from nuclear weapon. He is very much against a nuclear weapon, and he also coronavirus also. He has a strong opinion. This is more details of the grammar. This is the regular language, what is deterministic, which is done by the finite state machine. Then the next higher level, there is deterministic context-free language. Here, this parenthesis grammar, properly nested parenthesis can be detected, and another form is a to the power n, b to the power n. These two particular language, it can be easily detected by a deterministic pushdown automata, and all our programming languages comes under this. And I'll come to this picture of ambiguity. All deterministic context-free languages are unambiguous. You cannot design a grammar which has ambiguity in the deterministic context-free languages, but that cannot be said about this non-deterministic context-free languages. The best example of non-deterministic context-free languages, I'll come the palindrome. Two types of palindromes are there. One is odd palindrome, another even palindrome. So from this side, and if you from the reverse side, the same terminals would come. So this is the two regions mainly. The main the issues between the deterministic computation and non-deterministic computation is non-deterministic computation can take any of the path. If one of the path is got accepted, then the whole path can be accepted. This is very difficult to realize in hardware, but it has proven that in finite state machine, this deterministic computation and non-deterministic computation, it will take a longer amount of time, and it is unrealizable. But all non-deterministic computation can be converted to deterministic computation, but that cannot be said, unfortunately, about the PDA. Pushdown automata, the deterministic pushdown automata and non-deterministic pushdown automata, to different ball game. Non-deterministic pushdown automata is more powerful, but it can recognize more different type of language like palindrome, odd palindrome, or even palindrome. Here I discuss about the rules of the grammar. You know this is the variable portion, and this is the regular grammar. The left hand side should be a single variable, and some books call it as a non-terminal, and the right hand side any string. But in regular grammar, this string can be this form, like a terminal or a terminal at a variable. This is called right linear grammar. And it can be others. The variable can before and terminal can, that's the left linear grammar. In a single grammar, both left linear and right linear cannot be there. Then it will go to the next stage, the context-free grammar. The context-free grammar also, the left hand side is a single variable, but right hand side no such restriction. It can be consist of terminals and variables in any way juxtaposed. So, but remember, both this case there should be a single variable, but in context sensitive grammar, here we say that is the we have the we have a context, that is the here the no context is a context that it can be any variable, a terminal, and right hand side can be anything. This is the same thing I've told in different. This is a FSM regular grammar. This is context free. Here comes the a to the power n, b to the power n. This deterministic context free languages, so that you can have design a PDA where when the zeros is coming, you push them onto the stack, and when the 1 is coming, you pop each 0 and matching what 1 1, and you can design a machine very easily. Deterministic PDA, that is context free grammar, and this is the rules of the grammar. S is the start variable and S can go to epsilon, and this is a context sensitive grammar. You see here the variables can have a context A0 and A1, and here the languages come a to the power n, 0 to the power n, 1 to the power n, 2 to the power n. These are the rules. Why I call it context sensitive? It obvious from these two rules. There is a with context the variables is there. The context free grammar here, the push down automata, two types of push down automata. One is deterministic push down automata, that is deterministic context free grammar, and another is non-deterministic push down automata, that is non-deterministic context free grammar. And there is come the linear bounded automata, and this is the more higher grammar and the more higher type of machine, and this is a regular grammar which can be detected by finite state machine. So we are basically in this region, push down automata and the context free grammar. Same thing, the deterministic context free languages. Here you see the languages accepted by push down automata. Deterministic, that is the a to the power n, b to the power n, parenthesis grammar I will come, then I will come the XML, and languages accepted by non-deterministic PDA is basically, you can see, palindrome. The formal definition of context free grammar. In various books, some books is V for variable, and some books is a non-terminal. Both is okay, but you must know the context. This is V for variable. This is sigma. This is a set of full terminals. There should not be any V and sigma should not share a single one, so that no variable should be in the alphabet. This is the alphabet consists of terminals as usual. This the P is the production rules, and S is the start symbol which must be from variable. And these are the rules. A goes to alpha, a string of terminals and variables. It can go to epsilon also. The null string can be there. This is an example I take from CFG. These are the rules. A is the start variable, and it generates this language 0 to the power n hash 1 to the power n. You see this is the derivation, and you can see basically the parsing tree which is unique. You cannot have another parsing tree. This is the main characteristics of deterministic context free grammar. Here I have shown the same example from the CFG. So this is the language generated by the grammar 1. This is the grammar 1. A, again I repeat, is a start variable, and B is the marker of the midpoint. Another example from CFG. Here I have shown the actually context free grammar. Take the example, Noam Chomsky has invented this from our English language. That's like sentence, noun phrase, verb phrase. Then the noun phrase can have a complex noun, preposition phrase. Even verb phrase can have complex verb, preposition phrase can have complex noun. So it is a recursive in nature. Say the complex verb can have a noun phrase also. A noun phrase is there also, and it can be in the verb phrase also. That is a phrase structure grammar basically. So it can be recursive definition, which cannot be done in regular grammar. And you can generate, this is the terminals, A, THE, boy, girl, flower, touches, likes, sees, and there is a 10 variables and about 27 terminals. 26 alphabets and space characteristics. These are the 18 rules, and you can generate the sentences. You can see the details in the CFG's book, which is available in the Adobe format. There is another example of the CFG. This is a parenthesis grammar. This is the grammar and this is the rules, and you take this A and B as a parenthesis, and you will see here the parenthesis grammar. You can generate the parsing tree always be the unique. You cannot have a different parsing tree. You can design a context-free grammar by combinations of the rules, because the union of context-free grammar, deterministic context-free grammar is always a deterministic context-free grammar. So you can, like a language, you want to design a language like 0 to the power n, 1 to the power n, union of 1 to the power n, 0 to the power n. This is a deterministic context-free grammar. This is also deterministic context-free language. Sorry, it's a language. This is also deterministic context-free language. And union of it, it is again a deterministic context-free language. How to make the production rules? You make a first production rules of this part, like S1, 0, S1, this is the production rules, and this is S2, another starting symbol of this production rules, and you create a separate start variable, and you have an optional S2, S1 or S2, S2, and then all these rules combined. Then the grammar of this language, there's a union of these two languages, you can generally generate. This is the grammar of the union of 0 to the power n, 1 to the power n, and 1 to the power n, 0 to the power n. This is the grammar. This whole example is I am quoted from the Michael Six's book. So how to design a context-free grammar from simpler deterministic context-free grammar. You just, I repeat, you just create two different grammars and make a start symbol goes to S1 and another option, another is S2. Yeah, this is ambiguity. Ambiguity is everywhere. The literature is there. In poetry, ambiguity sometimes makes your song more double meaning. But here in programming language, that is completely no. Say you call me a cab, or okay, where you the girl asks, okay, you are a cab, so call me a cab, or confused, like half-baked chicken or half-baked chicken, two different meanings. So this is okay. In English literature, can it be there? It can be there, but in programming languages, it cannot be. So the context-free grammar, a grammar can have an ambiguity, but a language, if you say a grammar has an ambiguity, doesn't mean the language has ambiguity. You have to design a grammar such a way that language should not have ambiguity. So I can say that a language can be generated by more than one grammar. If one of them I can make it no ambiguity, then the language is non-ambiguous. But if I found that all the grammars are ambiguous, then you can say that inherently ambiguous language. Fortunately, inherently ambiguous language, it doesn't come on the deterministic context-free grammar. Okay, let's go on. Here you see this is the rules of the grammar, and if you see this rule, see this is the comes by properly applying this one, and this is another derivation. We come to the same terminals, but the two different ways. So this I say the always go for, there's a left hand derivation, left symbol, you first take the left symbol derivation, another you take a different rule. So there are two different ways you can come to this. So this grammar I can say is a ambiguous grammar. I cannot say the language is ambiguous. I have to tweak the grammar so that it can be unambiguous. Let's see, this I quoted from the Michael Six's book. So there cannot be, there should be, if we go for left derivation first, if we go for always left derivation, then it should come only one and only rule, no other rule. So your parsing tree should be unique. Here it is not. Here this is ambiguous. So I have to, this is ambiguous, I have to change the grammar. in such a way like this. I've introduced a new rule so that it is unambiguous. So language, I have to modify a grammar so that it is unambiguous. So when I cannot design a grammar which is not ambiguous, then I call the language is ambiguous. Here we see that by simply, this is a particular grammar which can generate the palindrome, but if we just incorporate the parenthesis onto it, we change the rules, then it can be detected by deterministic context-free grammar. And by just incorporating the parenthesis, we make is a non-deterministic context-free grammar to deterministic context-free grammar. This I also quoted from Michael Sipps's book. This language rules in non-deterministic context-free grammar. That here, this is a deterministic context-free grammar. I incorporated this parenthesis onto it. So I'm changing the grammar little bit, but it will be unambiguous. If it's unambiguous, then it can be easily detected by deterministic context-free, deterministic context-free and by deterministic push-down automata, which is very easy to design. Non-deterministic push-down automata is very difficult to design. Our XML, the way the internet exchange format, this is another example of deterministic context-free grammar. You always see take it as a parenthesis, always see the parenthesis open and parenthesis end. This is all XML document can be by deterministic context-free grammar. This is one interesting example, context-free language inherently ambiguous. Whenever you see this kind of language, a to the power I, b to the power j, c to the power k, either I equal to j or j equal to k, then it is definitely a context-free grammar. Whenever we say I equal to j equal to k, then it is a context-sensitive grammar. There is no way that is a context-free grammar. But when I say I equal to j or j equal to k, so you can design a non-deterministic context-free grammar or non-deterministic push-down automata which always guess one of it, either y is equal to j or j is equal to k as a non-deterministic, which is inherently ambiguous language. So this is a good example of inherently ambiguous language which can be accepted by only non-deterministic push-down automata. You cannot tweak the rule into a deterministic context-free grammar. And this is also example is from the Sipps's book. It is available in the Sipps's book. Please see this. Same example, either I equal to j, if I equal to j, it can be deterministic context-free. This is also deterministic context-free, but whenever I go for or, it has to always a deterministic context-free have to always guess correctly which one I should take. So this cannot be done only by non-deterministic push-down automata. So this is inherently ambiguous. Another example of inherently ambiguous, a to the power n, b to the power n, c to the power n, d to the power n is required, or union a to the power n and d to the power n. Always a push-down automata has to guess whether I should a to the power n, b to the power n, c to the power n, d to the power n, or a to the power n, d to the power n and b to the power n, c to the power n. So always they have to guess. So these all are examples of non-deterministic context-free grammar, inherently ambiguous grammar. This is difficult by any realizable hardware, and non-deterministic push-down automata is made for this. One interesting statement I used to make, that is, there is no algorithm to convert automatically any ambiguous grammar to unambiguous grammar, accepting the same language. So there is no algorithm, you have to just tweak into it. This is another way is undecidable. There is no such algorithm. You have to just go for it. There is context-free grammar. There is one famous form is Chomsky's normal form. He has actually designed the grammar. The Chomsky's normal form says the left-hand side should be single variable and right-hand side should be only two variables or a single terminal. And there is no rule you should allow it so that any variable other than the start variable can go to epsilon. Only start variable can go to epsilon. So this is mentioned here. The left hand side should be a single variable, right hand side two variables, only two variables, no one variable with a terminal. It should be always two variables and or single terminal. And no epsilon will be allowed. If you incorporate into the epsilon into the grammar, you can only allow only the start variable. Only start variable can go to the epsilon. No other variable can go to the epsilon. Same thing in different ways. You should same thing with A, B, and C may not be start variable. Only start variable can be only the epsilon, otherwise not. This is John Hopkins' book into the automata theory. Same thing, you go through it. Michael Sipser, John Hopkins, these are the two legendary books. It's good books, you should read. So why go for Chomsky's normal form? Because the variable can have at most two branches or one. So you cannot have multiple branches, and maximum you have a depth, maximum you have two branches, and maximum if you have n terminals, maximum 2n minus 1 steps you can parse the string. That is the strength of this grammar, and it is more understandable by a program. If we can think of it as a tree format, binary tree. Binary tree is always easier to code, and in the program can have only two things, if then else, and you can say binary tree, so it can be easier for a program to understand, to parse the language if the grammar is given to it in Chomsky's normal form. Whenever you parse the language, you have to give in the language in a grammar form input to the parser. You can generate automatically the parser from this yet another compiler, a particular program is there to generate the grammar, to generate the parser. Sorry. This I have mentioned. What is the Chomsky's normal form? There's another forms are there, that is Greifach normal form, and another is S grammar, that I'll cover in my later lectures. The Chomsky's normal form is very vital. Remember, all context-free grammar, including the deterministic context-free grammar or non-deterministic context-free grammar, can be converted to Chomsky's normal form, all. But no variables can go to epsilon. Only start variable can go to epsilon if there is a string accepted by epsilon. String has to be accepted by the language. And same thing, the Greifach normal form, we'll come to this later. So beauty of the Chomsky's normal form is that you can always, if there's a string of n letters, you can exactly 2 to the power n minus steps. So I believe I can communicate to you. So later we can see. Thank you.